Okay, we're going to introduce the notion of one-to-one. We may have done this earlier, I think, in one of our counting arguments, when we try to prove two sets have the same number of elements. But anyway, a function is called one-to-one if, when any two values, for any a and b, if f of a, if phi of a is equal to phi of b, the only way that could happen is if a equals b. Again, this notion comes up when you look at which functions have inverse functions. That's sometimes where one-to-one is defined. Graphically, it means that something would pass the horizontal line test. And so we have a proposition now. If we have a group homomorphism, not just any mapping, then the mapping is one-to-one if and only if the kernel of the mapping is just the identity. So again, the kernel, recall, is a set of all elements in the domain that the function maps to the identity in the other group, the group that's part of the range, or the group that contains the range. So let's see why this is the case. So first, let's assume phi is one-to-one. Is one-to-one. So what does that tell us? That tells us that how would we then go about using it? We want to show that E of G is the only thing in the identity. Well, we know that phi of EG is equal to EH. EH is the identity of H. We proved that earlier, and that's just the definition of that being in the kernel, of an element being in the kernel means it gets sent to the identity. So we at least have E is inside the kernel, but why is that anything? So let's take any element in the kernel, and what do we have? We have that it gets mapped to EH. But then what does that say? But then since by that other equation we know that so phi of G is EH, but that's EH is also phi of EG, so phi of G equals phi of the identity. We're assuming mapping is one-to-one. So that says G must be the identity. G was just an arbitrary element in the kernel, so that tells us that the kernel of phi has to be entirely contained within this one element set of the identity. And so clearly we have the other containment, so these two sets are equal. Then let's prove it in the other direction, that if the identity is the only thing in the kernel, the identity is the only thing in the kernel, then the mapping is one-to-one. So now, assume that the kernel is just the identity. So we want to show it's one-to-one. So how do we show it's one-to-one? We first, to show phi is one-to-one, take G, or I guess I used A and B in the notes, so I might as well stick with A and B. Take two elements of G with phi of A equals phi of B. We want to show that A equals B. Well, this equation leads to what? I can multiply on the left on the right by B inverse, or by phi of B inverse. To give me the identity in the set H. And then, remember, we've seen a homomorphism, the inverse comes inside, and then we can multiply both of them. So this would have to then equal B of H so that tells us B inverse A is in the kernel of phi, but the kernel of phi is just the identity element of G. So we would have B inverse A has to equal E of G. And so if we multiply on the right by B, that would just get the identity, so that would cancel. So B inverse A equals B, B, G, or just simply A equals B. Thus phi is 1 to 1. So we prove both implications of the theorem that's required, as required. We now give an important definition. A group isomorphism is a group homomorphism that is both onto and 1 to 1. And if phi, say, from G to H is a group isomorphism, then we say G is isomorphic to H. And we really write G, H, and we put an equal sign with a single tilde, twiddle on with that. So that's notation for isomorphic. So we claim This relationship isomorphism is an equivalence relation on the set of all groups so let's prove this claim. So the first thing is reflexive. Let phi of G equal G for all G in H, all G in G. Then phi is an isomorphism from G to G, so G is isomorphic to itself. I think in the notes I actually proved some of the details, but certainly it's multiply G times G prime. Well, that's the same as first taking G times G prime and putting them into the function, right? Is it 1 to 1? Suppose phi of A equals phi of B. Well, phi of A by definition is A, phi of G by B is by definition B, so A would equal B as well. So you can check the notes for those details. Symmetric. Suppose G is isomorphic to H, with phi being one such mapping. Or one such isomorphism. What we're going to do is we're really going to define, very similar to, again, from the notion of pre-calculus, the inverse function. So we'll define this function of phi inverse. So we define, I'll even use a different symbol. I think I called it rho in the notes. But let's actually define phi inverse from H to G by what? By phi inverse is equal, phi inverse of H is equal to G, where, as I hit the end of the board, where what is G? Where G in G is an element with phi of G equal to H. Such a G exists since phi being an isomorphism is onto, and so its image, phi of G, is in H. In other words, anything in H has to be the image of something we put into phi, an image of an element of G plugged into phi. So there's a well-defined this issue right off the bat, right? The question is, suppose phi of G equals H and phi of G prime equals H as well. Because you want the function to be well-defined. So then on the one hand, by our definition, phi inverse of H would have to be G. But on the other, by our definition, phi inverse of H would have to be G prime. So what do you know about a function? A function, but again, pre-calculus, is a rule that, one way to define it is a rule that to any given input assigns exactly one output. So h is the same, we better get the same output for it to be a function, but that's no problem, right? Because what? Phi of g is equal to h, which is the same thing as phi of g prime, and since phi is 1 to 1, see we've used the onto, now we use the 1 to 1, g has to equal g prime. So we have a well-defined function. And then the rest of it should be pretty easy. Often in these proofs, sort of the, with homomorphisms and isomorphisms, once you can show something that's well-defined, the other parts are usually not too bad at all. So let's show y is onto. So let's first show that now it's well-defined. Why is it a homomorphism? Take any two elements in H. Since phi is onto, that has to mean there have to be two elements in G that phi sends to H, and the second element that phi sends to H prime. Well, what would phi inverse of H times H prime be? Oh, well, let me actually, what would phi inverse, let's look at it from the other side. Let's first look at the product. What would phi inverse of H times phi inverse of H prime be? Well, that's equal to G and G prime. But if now instead of looking at phi inverse, if we just look at phi of G times phi of G prime, times G prime, that's phi of G times phi of G prime. Phi of G is just H. Phi of G prime is H prime. So it looks to me like, therefore, so what does this mean? This means phi of G, G prime equal H, H prime means exactly that phi inverse of H, H prime is G, G prime, which we've just shown is equal to phi of H, or phi inverse of H, phi inverse of H prime. And so phi inverse is a homomorphism. Let's show that it's onto. Take any G in G, let H be phi of G, but by our definition, that's exactly then phi inverse of H would have to equal G. So phi inverse is onto. Finally, the one-to-one. Take so let's take let's see. Show that it's 1 to 1. So let's take, or let's assume to show it's 1 to 1. Let's assume that phi inverse of H is equal to phi inverse of H prime. So that means, so if phi of G equals H and phi of G prime equals H prime, this means G would have to equal G prime. So let's see. So actually, what would this say? Actually, let me say here. So remember what we're assumption, right? We haven't used our assumption yet. So thus, we would have that G is phi inverse of H. But if we're assuming that's phi inverse of H prime, which we saw as G prime. So we have that assumption. So what does that mean? Then if we take this, so we would have phi of G equals H, and also phi of G is equal to phi of G prime, which is H prime. But now phi is a well-defined function, right? So if we stick G in, we have to have what comes out being the same, right? So H has to equal H prime since both equal phi of G. Therefore, phi inverse is 1 to 1. And so we've just shown it's onto, it's a homomorphism. And now we've shown it's 1 to 1, so it's got to be an isomorphism. And so that shows us that H is isomorphic to G. So that's the second property that twiddle is reflexive. Well, this isomorphism, this symbol is not reflexive, it's symmetric. Finally, for the transitivity, we assumed G is isomorphic to H, and H is isomorphic to K. So we have two isomorphisms then phi from G to H. I'll use psi from H to K. So what's a natural way to try to, again, to show transitivity, we have to try to prove that G is isomorphic to K. So a natural method would be a function, right, of composition. So let rho be psi composed with phi. So rho of G would equal psi of phi of G. Again, we're using the notion of function composition. Another isomorphism is really there's a lot of connection between some of the material and pre-calculus, especially this notion of one-to-one. But now with the additional group structure, that one-to-one has a meaning of the kernel, and being that the kernel just consists only of the identity. So certainly this is a function, right? What do we have? We have phi of G is in H, so psi of phi of G is defined. Let's show it's an isomorphism, so for all A, B, and G, we look at rho of AB, so that would be psi of phi of AB, but phi of AB is a homomorphism, so that would be psi of phi of A times phi of B. But now we split that up, that's psi of phi of A, psi of phi of B. Because psi itself is a homomorphism. But this is exactly rho of A times rho of B. So we have a homomorphism. Then we're trying to show G is isomorphic to K, so we constructed this rho from G all the way to K is a homomorphism. What about an isomorphism? So let's try to now show that it's onto. So take any, show it's onto, we have to take any little k and k. Well, what do we know? We know psi is onto. So since psi is onto, there's a psi of h is equal to k for some h and h. But now, phi from G to H is onto, so there is a G in G with phi of G has to be H. So what's that going to tell us? That's going to tell us that if we look at rho of G, that's just going to be phi of, psi of rho of G, which is going to be psi of H, which is just K. So rho is onto, because we found in G and G, if you give me any K and K, I can find an element of G that rho is going to send to that. How about one-to-one? So here we use the characterization of the kernel of rho. We'll show the kernel of rho consists only of the identity of G. So let X be in the kernel of rho. So rho of X has to be the identity in K. By definition, that means psi of phi of G, of phi of X has to equal E of K, the identity element of K. But remember, phi is one-to-one, so this means that phi of G has to be in the kernel of psi, which since psi is one-to-one, from H into K, the kernel of psi only consists of E. So I guess that tells us phi of G is the identity element of H. But again, so what does that tell us? That tells us G is in the kernel of phi. Remember, the phi was one-to-one, so its kernel has to just be E of G. So X must be equal to E of G. So we've really shown, so the kernel of rho, if something's in the kernel of rho, the only way that could happen if it's the identity element E of G. Therefore, so here we use the thing that if something was one-to-one, the kernel was the identity. We've used that now. Let's go and remember that we proved that if and only if. So in the other direction, since the kernel of rho is only the identity, rho is one-to-one, and thus an isomorphism So what have we shown? We have shown transitivity. So we've shown that if G is isomorphic to H, and H is isomorphic to K, in fact that's got to imply that G is isomorphic to K. So we have an equivalence relation. So you can think of, if we look at all groups, this isomorphism is a way to sort of break up, partition the groups into different ways. So let's prove some theorems. So a theorem, let G be a cyclic group. So it's got to be generated by a single element, by all powers of a single element. If the order of A is some number m that's finite, then G, which is just cyclic subgroup generated by A, in fact, has to be the integers mod m. If G is equal, if the order of A is infinite, so G is an infinite cyclic group, it's got to be the integers. When I say got to be, up to isomorphism. If the order of A is infinite, then the cyclic group generated by A, this group G, is isomorphic to all of the integers. So let's look at a proof. Let's look at the first. Suppose the order of A is infinite. Then, and this is actually true, a lot of this proof can be adapted in both cases. G, you can think about it as all powers of A, where K goes through the positive integers. And those are infinitely many. Turns out if you have a finite cyclic group, what you can do is you only have to worry about the powers from 0 up to m minus 1. Okay, so what do we define? Let's define phi from G to Z by, well, what's a typical element in G? A typical element in G is A to the K, so phi of A to the K is just going to be the integer K. So even maybe there's a question of, is it well defined? But remember, in a cyclic group, what we can show is that the order of, or if A to the K equals A to the J, then these two integers are equal. The reason for that is otherwise, you look at e to the k minus j multiplied by the inverse of j, each side by the inverse of a, j times, you would get this would be the identity, or you could go in the other direction, j minus k would be the identity. One of these two is positive, so you have a to a positive number being the identity. That can't happen in an infinite cyclic group, right? Because if that was the case, then there would only be finitely many of elements in this set. So a positive, if a to the k equals a to the j, for k not equal to j, then a raised to a positive power would equal the identity. But the order of A is infinite, so that's a contradiction. So there's no the long of that is just there's no well-defined this issue. There's only one way to write an element of the group as A to the K. So is it a homomorphism? Well, phi of A to the K. So let's maybe put a few more details in here. So if we take any two elements G G prime in G. Then we have some integers, say K and J in Z, with G equals A to the K and G prime equals A to the J. Again, that's because the group is cyclic. So, and generated by A. So, phi of G prime would just be phi of A to the K, A to the J, but we have the properties of exponents is just added to that, but that is exactly going to be A to the K, or sorry, K plus J by definition of our mapping. And then K is exactly phi of A to the K, and J is exactly phi of A to the J. So we have a homomorphism. Again, remember that here, we think of G as being an abstract group, so we write it multiplicatively. That's why we're using power notation for the cyclic group. As a concrete group, though, the group or operation in Z is addition, so that's why this represents the product, if you will, the two elements met, you know, the result of applying a group operation to those two elements. Why is it onto take any integer Z, phi of A to the, any integer R and Z, phi of A to the R equals R, so phi is onto. Again, sometimes onto looks pretty easy because you just kind of have to produce a single element that gives you an arbitrary element in the set here. So that's why it's onto. Why is it 1-to-1? So let X, which is some A to the K, be an element of the kernel of my mapping phi. So phi of A to the K is equal to 0. That's the identity in the integers. So K has to equal 0. That is what phi to the K is, right? Phi to the A to the K is equal to K. So X, which is A to the K, is really A to the 0, which is the identity. So we've seen that the phi is 1-to-1. Since the kernel of phi consists only of the identity. We'll just write EG. I don't have to say EG, I'll just use E, because the other group H in this case is the integer Z, so I don't need a symbol for the identity, it's just 0. 0 is the identity. So we have that result. So it's 1-to-1, it's onto, it's a homomorphism. Therefore, the cyclic group A, which is G, is isomorphic to the integers. The integers mod n can serve as a example for that. And a lot of this proof can be adapted in terms of how we define it. The only difference is with the integers, if you look at the powers of the generator, the positive powers are all distinct. So to get the inverse, you need to take the negative powers of A as well. And then you also need to throw in the 0th power of A, which is the identity. So let's look at this. Recall that if the order of A equals M, then G, which is the cyclic loop generated by A, is just, again, A to the K, but now we can pick A between 0 and M minus 1. And again, Zm, these are all equivalence classes of integers, say, n, where n is between 0 and m minus 1. So what's a natural mapping? The natural mapping is, let's look at phi. A typical element of G is just a to the x, a to the k, and we'll define it by the equivalence class determined by k. So it's certainly well defined because all of these are distinct. So we only have to look at these elements. Each one will go to k. There's not a question of two different representatives. Let's look, why is it a homomorphism? Again, it's just the properties of exponents. A to the k times, the second element would be maybe a to the l. Or I'll say j, a to the j. Equals let me be careful with this. Because what is a group operation? The group operation, this phi of a to the k, that's an element of Zm. So the group operation Zm would be addition. So we want to check what this is. And that's just the class determined by k, and that's the class determined by j, but in the integers mod n, just like in any factor group, the way we add cosets is we just add the representatives, or we use a group operation. But again, this by definition is exactly phi of a, k to the j. So this is a homomorphism. We can actually show that we can define it on any power, even though we only have to define it in terms of those k. But if these two are equal, then this is the identity. And this is the identity. But remember, the n is the smallest power, so if a to the n, if any a raised to any integer, if that gives you the identity, that means the order must divide it. So m would have to divide, say, x minus j. Actually would divide both. X minus j would divide both of those. But that's just what congruence means, right? Those are elements of Zm, these equivalence classes, so that those two determine the same class. And so, but that's just phi of ak, and that's just phi of aj. So any well-defined, this issue is not a problem. I mean, technically, its definition, we don't need well-defined this because these are all the elements. But you may just want to go, can I still apply the properties? What if x plus j is not less than n minus 1, even though k and j are? But if that's the case, you see, it doesn't matter. We can define this mapping for any integer, not just between 0 and n minus 1 because of that. Okay, so we've got the mapping is well defined, and it's a homomorphism. Why is it onto? Again, onto is usually pretty easy. Take any k in Zm, any class determined by an integer. Then, of course, phi of k will map to that class. To that class, so phi is onto. How about one-to-one? If we have some arbitrary element, a to the k, in G, that's in the kernel, that would mean phi of a to the k would be the identity, which is 0, but phi of a to the k, by definition, is just the equivalence class of k. So the equivalence class of k is equal to 0, so that tells us the order of m, of the integers mod m, must divide k. So k equals s times m for some integer s. And so if we look at a to the k equals a to the s times m, which is a to the m times s, but this is just e. So this shows us that if we take any element of G that's in the kernel, phi of G equals, really that shows us the kernel of phi is contained in and therefore equal to the identity. And phi is 1. And that's an isomorphism, so establishing that the integers mod m are isomorphic to every cyclic group of order n. So a consequence of this are the original groups way back when we first introduced some groups. We found cyclic groups of any order for the integers for the roots of x to z to the m equals 1, the complex roots of unity. That was as a multiplicative group. But now we see that was a cyclic group of order m, so it must be isomorphic to the integers mod m. Okay, so we're now going to prove what's called the first isomorphism theorem. So let phi from G to H be a group isomorphism. Oh no, let me get, It's not. It's the first isomorphism theorem, but it's actually just a group homomorphism. So we just have a group homomorphism. Then if we look at the image, phi of G, that's isomorphic to the factor group formed by G mod the kernel of phi. So we're going to prove this in a second, but I'm doing the notes like to give you an application. Call in the notes that if G is the Heisenberg group, one, A, B, C, we already constructed a phi from G to Z2 cross Z2 with phi, which was onto, so phi of G was equal to Z cross Z2. And remember, what was the kernel of phi? Kernel of phi, we sent these two to a pair, so these two were 0. The kernel of phi was exactly the center of G. So by the theorem of above, we would have that G, the Heisenberg group modded center, is isomorphic to the group that's made by taking the direct product, the Cartesian product of Z with itself, or the integers with itself. So let's define this mapping. So what we'll do is let phi go from G to H. Okay, now this is in the proof, so G is not the Heisenberg group. G is just any arbitrary group. And let, so we don't have to keep writing kernel, N is just the kernel. So instead of writing kernel phi, we'll just write N. So let's define a potential isomorphism. Let H be an element of phi of G. So there exists a G in G with phi of G equal H. We want to define a second mapping. I'll use rho again. Rho from phi of G to let's map it to this coset group. G mod the kernel, but I'll just write G mod N, so I don't have to write kernel, by rho of a G, so phi of G, so I gotta say, what's a typical element of phi of G? That's an H. So rho of H is equal to G times n. So take this, so in other words, if h is in the image, h has to come from some g. So what I'll define, I'll say rho of h is going to be that coset determined by that g. Now you may say, wait, left coset or right coset? But recall, kernels are normal. N is normal. So Gn is equal to Ng. The left coset determined by G is the same as the right coset determined by G for every element. That's why we have a normal subgroup. I mean, after all, for this to be a map from a group to a set, we need these both to be a group. So we need a factor group you can only form when you have a normal subgroup. That's the only time that the cosets will form a group on the multiplication. So again, there's a well-defined decision. So say you have two G's, there exists a G and G prime. In G with H equal to phi of G, but also H equal to phi of G prime. So we'll look at that and see, to show, so then we have rho, on the one hand, rho of H would be equal to the coset determined by G, but also on the other hand, rho of H would be equal to the coset determined by G prime. So if a function, if we put the same thing in, we can only get this, we better get the same thing out. I mean, a function may have different things can go in and give you the same thing can come out. But if one thing comes in, goes into a function, we have to have the same output. So what do we know though? Well, both phi is equal to h, so we have phi of g is equal to phi of g prime. So that's going to give us what? That's going to give us, if we multiply on the left by phi of g prime, so left multiply, not by phi of g prime, but say phi of g inverse to get that E sub h is equal to phi of g inverse times phi of g prime for, well, I'm not even going to say it. It's clear what E of h is. That's the identity element of h. But again, using two properties at once, we can move this inverse inside. That's a property of a homomorphism. And then we add a multiplication. We could multiply first and then put inside the homomorphism. That's a property. So we have G inverse times G prime is the identity. That tells us that's in the kernel, which we're just calling n. So G inverse G is an element of n. But that just tells us G and G prime determine the same coset. And so, but what's that? That's exactly rho of h agrees. Agrees with either using G or G prime. So we've got a well-defined function. And hopefully you see why I had to make this argument. Again, that's because I'm defining my map and row based on a choice of an element that phi sends to H. I have to show that my definition is independent of the element G. And that's what I just did. Okay, next let's show why rho is a homomorphism. So we can take any two elements in phi of G. So say rho of phi of A times rho of phi of B. And by definition, that's AN times BN but that's ABN let's be a little careful here. So what exactly is this product here? This is, I've really taken them separately. So this actually is, AN is separately rho of phi A, and BN is rho of phi of B. And so that's equal to these two separate cosets, right? I'm plugging in these, I'm evaluating these first, so I'm getting my cosets first, then I'm multiplying, that's how I multiply cosets. But this is just going to be rho of phi AB, because that's my mapping, right? I look at phi of AB, that's a rho of that is a coset determined by AB. But rho is a homomorphism, so that's rho of phi A times rho of phi B. So rho is a be careful here. I'm just using the property that phi is a homomorphism. So phi of AB is phi of A times phi of B. That's still going on inside the parentheses, inside before I evaluate that at rho. So if we look at what I've shown, let me just restate it, connecting the two ends of the board, I've shown that rho of phi A times rho of phi B is equal to rho of phi A times phi B. So again, I didn't introduce an auxiliary variable. You could have sort of like in this is your x and this is your y. Right? Because the typical element that I'm putting into rho is in the range of, it is in the image of phi. So a typical x that I'm going to stick into rho has to look like phi of some A. So we have it's a homomorphism. What about the rest of it? How about onto? Usually, often onto seems like you don't really do anything, and I think this probably be a case here. Take any element phi of NH in G mod N, and of course G is in G, then phi of G is certainly in the image of G. So phi of little g is in phi of G, the set. And if here, maybe I'll introduce H equals phi of G. By definition, what is rho of H? It's just going to be this G coset determined by that G. So rho is onto, because if you give me any coset, Gn, I found an H in the image in phi of G that I can plug into rho. Careful, that is rho, so I believe I've been good with my functions up till that point, or to my mapping. So rho is the new mapping we create. The idea is phi is some homomorphism we have just from G, only from G to some set H. So what we do is we create a different homomorphism from the image of that homomorphism, and it goes into the coset group formed by G mod the kernel of that original homomorphism. So then you look how that original homomorphism is incorporated into our definition of rho. First of all, the fact that the only things we put into rho have to look like phi of G. And then also, what the image is we look at the cosets mod the kernel of that mapping. Okay, so we have a homomorphism, so on to 1-to-1. And what definition did I use? I think I used the regular definition of 1-to-1, where we assume two things are different. So assume H and H prime are in phi of G, with rho of H equaling rho of H prime. So since H and H prime are in phi of G, that means there exists two elements, G and G prime, in G, that phi will map that to H, and phi will map G prime to H prime. And so rho of H would just have to be Gn, and rho of H prime has to be G prime n. So if, by assumption, we're assuming rho of H equals rho of H prime, so these two are equal, so by our assumption we used to prove 1-to-1 that the image is equal on 2 points, we would have Gn has to be G prime of n, or G inverse G prime has to be an element of n, which would mean phi of G inverse G prime would then be the identity right? Because remember, n is in the kernel. And so that's going to, as before, we can see that's going to lead to phi of G equals G prime, or H equals H prime, and so phi is 1-to-1. Again, the reason for that is this is a homomorphism, so it splits up. So you would get phi of G prime times phi of G inverse times phi of G prime. This inverse comes out, so that's really the phi of G inverse. Then we multiply on both sides and get H. So maybe I should run through some of that. We have that equation. That's going to give us this. And so that will give us that. So we've got a one-to-one and onto, so we've proven the theorem. Therefore, G mod n, that factor group, is isomorphic to phi of G, which is the statement of the theorem. Okay, so let's prove another theorem now about what isomorphism group, what you might expect about isomorphism, groups that are isomorphic. And that's basically, if you put an element into a isomorphism, the order is unchanged. So here's a theorem. If phi from G to H is a group isomorphism, then for any element of G, the order of phi of G is equal to the order of G. The order of an element equals the order of its image under an isomorphism. Okay, so let us prove this. Let us prove only in the case that it's finite. But it's true in the case where it's infinite. If you have an element that has infinite order, then under an isomorphism, it must also have infinite order. So we prove only in the case where the order of G is finite. So if we look at phi of G to the m, something we'll just take informally that it's clear it must be proven by induction. If you have a product of two elements under homomorphism, you can multiply them first. If you have a product of any amount of elements, you can all multiply them together. So this is phi of G to the m, which G to the m is just the identity element in G, and then by properties of homomorphisms, that has to be that element. So what does that tell us? We may be tempted to say that's enough, but this means that M has to divide the order of G. Again, that's really sort of a consequence of Lagrange. Right? Remember, M is the smallest. The order of this is going to be the smallest positive integer. Oh, let me take that back. No, I don't think I've got my... M, this raises the M power takes you the identity, but there may be something smaller. So the actual order is the smallest positive power. So this means that the order of the image divides M. And again, we've proven this before, that if you raise something to a power, it takes you to the identity. That doesn't mean it's the order. The order could be something smaller, and in fact, the order must be a multiple. Right? Again, the proof of this, if you recall, is let's call this K. If K divides M, if it doesn't divide evenly, there's some remainder that's less than K, but that'll ultimately, if we use that to the M, takes us to the identity, that's really going to mean that something less than K, the remainder, if we raise it to the remainder, we also get the identity. So that was, we proved that in kind of in our cyclic groups, that in general in a group, if G to the R is equal to the identity, with R positive, then the order of G divides R. I guess we don't really even need it positive, but it's certainly true if R is 0 as well. So that's actually true for any group homomorphism. But why are they equal? Well, here's where the isomorphism comes into play. So, on the other hand, if we look at okay, so let me do that. Let K be the order of phi of G. Then that means phi of G to the K is the identity in H. So phi of G to the K has to be E of H. But now, for the first time, we use an isomorphism, but phi is an isomorphism, so phi is 1 to 1. So the kernel of phi is just the identity of G, and therefore phi of G to the K is equal to EG. basically, I should have maybe followed up. If phi of g to the k equals EH, we can say that means g to the k is in the kernel of phi, but phi is 1 to 1, so the kernel of phi is equal to the identity, and so that's h. And then by the same remark, so the order of g divides k. So now we've got this other division. So this equation, this divisibility relationship holds for any homomorphism. We get the reverse divisibility when we, if it's an isomorphism. Okay, so we're going to close with a couple of examples about some the unitary group of on the matrix, the group of units on the multiplicative group of the integers mod n. Just actually pull out a corollary, really, of the proof. Let phi from G to H be a group, forget about an isomorphism, just a group homomorphism. Then the order of phi of G divides the order of G for all G and G. So that was true for any homomorphism. Okay, so the proof, we'll just say proof, just did, done. So now recall, let us look at UN, the multiplicative group of units of the integers mod n. We're going to recall what was UM. UM was just all integers k, not from 1 to n, but integers k between 1 and m minus 1, and the important part, the GCD of m and k had to be 1. And under multiplication of cosets, or equivalence classes, the integers mod n. So let's look at it. What is the order of U8 has 4 elements. We saw from our Cayley table, every 4 element is abelian, and any abelian group of order 4 has to be one of two different groups up to isomorphism. It's isomorphic to, well, there was a cyclic group, so Z4, which is cyclic, or Z2 cross Z2, which could be thought of as the Klein 4 group. Each element is its own inverse. Okay, and actually those are all the groups. We just want to note there are no non-abelian groups of order 4. But really, in general, UM we know has to be abelian, so it would have to be one of those two. Well, which one is it? Well, by a theorem, Z4 is cyclic. It's got an element of order 4. So if UM is cyclic, it's got to be Z4. Otherwise, if it's not cyclic, it can't, if it was isomorphic, it'd have to have an element of order 4, so it would also have to be cyclic. But let's see if it is or isn't. So let's check it out. What is U8? I think we've maybe done some calculations, but let's check in U8. What is 3 squared is 9, which is 1. 5 squared is 25, which is also equivalent to the identity. 1 squared is 1, and then the only thing left is 7, which is really like -1. So that's the equivalence class determined by 49, which is also 1. So U8 has to be isomorphic to the Klein 4 group, Z2 cross Z2. What about U8? I think the order is let's look at it. What is UN? UN we've already done. Let's look at U16. What is the order of U16? It turns out to be 8. There's actually a formula. Let's see if we can use the formula. This is the order of U16 is just 2 to the 4th. And so what the heck is the formula for that? That's one way to do it is you look at 2 to the 4th, 16. Here, and then you have to take away 2 to the 3rd, so 16 minus 8 is 8. So there are 8 elements. And we can list them explicitly. I'll just count them off. What do we have? We have the all ones, so we have 3, 5, 7, 9, 11, 13, 15, and what did I say? I didn't say the easy one, 1. So those are the elements. So one of the possible, any abelian group of order 8 is isomorphic to one of which one? Well, let's see. It could be a cyclic group. That would be all 16, Z8, 8-element cyclic group. You could look at the product of the 4-element cyclic group with the 2-element cyclic group. Or you could look at the product of 3 2-element cyclic groups. Again, remember the way we found the product of two groups, or the Cartesian product of two groups. What you would do is, this group, for instance, you add all ordered pairs, you add mod 4 in the first component and mod 2 in the second component. This group, you'd have 3 components, you'd add mod 2 in each of the 3 components. So let's try to see what happens here. Let's look at 3, say to the 4th, is 3 squared times 3 times 3. 3 squared is just 9, so it would be 9 times 3 times 3, which would be 27. But mod 16, 27 is 11, so it would be 11 times 3, which would then be 33, which is congruent to 1. So U16 cannot be isomorphic to which one? Well, this element, the 4th power is the first time 3 goes to the identity, so that element has order 4. But this group here, if you think about adding any 2 elements, every element here is going to have order 2. So this cannot be isomorphic to Z2 cross Z2 cross Z2, since if we add 2 elements, A, B, C, if we add anything to itself, and again, I should put bars around these, but I'm not going to. 2A, 2B, 2C. That's equal 0, comma 0 in this group. Now I will put the bars around there. Right? Because in mod 2, any even number is equivalent to 0, and certainly all of those are even numbers. So every element in Z2 cross Z2 has order at most 2. So our choices are narrowed down. So now we're down to 2 choices. So it's isomorphic to either Z4 cross Z2 or Z8. What determines which one it's isomorphic to? Well, this is cyclic. This group is not cyclic. Every element there, if you multiply everything, if you add anything here to itself 4 times, both components would be 0. So you wouldn't get, so that group could only have order 4. Or, every element in this group can only have order 4. The group, they still both have 8 elements. So really that determines whether it's cyclic or not. This is a cyclic group. So let's try to see whether it's cyclic or not. Let's see if we can find an element of order 8. Well, what is the inverse of 3? 3 inverse would be what? 3 times what would take you to the identity mod 16. So 23, 21, that doesn't work. That's 5. 3 times 3, it's not its own inverse. It can't be because it has order 4. Maybe is it 11? 3 times 11 is 33. So the order of 11 has to also be 4. Remember, every element has the same order as its inverse. So we don't bother trying 11. How about 5? Well, 5 squared is 25, which has order 1. So that that's its own inverse. 7 squared is also its own inverse, right? 49, which is 1. And so I think we've got it covered, right? There are 8 elements. Here's 1, here's 2, 3, 4. Certainly 1 won't work, is 5. Negative 1 is what? 15. So 15 squared should also have order, should be the identity, because 15 is really like negative 1, because 1 plus 15 is congruent to 0 mod 16. So what we have is then, this would be 225, and we'll just say that's equal to 1, even though I'm sure 16, well, we can do some long division. I'm not even going to put this off camera. I'll divide off camera. So 16 goes in 10 times, right? 16 goes into 15 squared is 225. So this would give us 65, and then times 4 would give us 1, right? So 225 is 14. 14 times 16 plus 1, which mod 16 is just equal to 1. So U16 is not cyclic. It does not have an element of order 8. Z8 is cyclic. It does have an element of order 8. So U16 cannot be isomorphic to Z8. So our only choice left then was Z4 cross Z2. So we'll conclude today's lecture right here.